Welcome. Today, we're going to make sense of inverse functions. So what exactly is an inverse function? So let's say that we have a function. Let's call it f of x. So let's visualize this. For any function, which in this case we're going to call it f of x, there is an input, which we use the variable of x, and there is an output, which we use the variable of y. Well, the inverse function, it will undo what the function of f of x did. In other words, the inverse function, it will get the variable of y that we got from f of x. And that variable, we can plug it into this inverse function, and it will tell us what was the variable of x that we plug in to f of x. So it does the opposite of f of x. So you can think of a relationship between a function and an inverse function as a full loop. We have some variable, we can call it x, and we plug into this function, let's call it f of x, and we're going to get a y out of it. Well, the inverse function will use this variable of y, and if we plug it into the inverse function, it will tell us exactly what was the variable of x that we use in the function of f of x. And we have a notation for inverse function. So let's say that we have a function, let's call it f of x. The way that we're going to write down the inverse of f of x, it's by placing a little -1 between the f and the x. And do not confuse this with an exponent. We're not raising f to an exponent of -1. This is just notation. So let's say that we have another function, let's call it g of x. Then the way that we're going to represent the inverse of g of x is by placing a little -1 between the g and the x. But again, this is not an exponent, this is just a notation. And so forward, if we have a function, if we call it h of x, then the inverse will have a -1 between the h and the x. So if we go back to our visual, instead of writing inverse, we can write f -1 of x. Now, what are some properties that inverse functions have? Well, one thing that we can say is that the domain of the inverse function is the range of the original function. So let's visualize that. Notice that what we're plugging in to our inverse function, it is the y value that we obtain from f of x. And the y value of f of x, it is a range of the function. And the second property is that the range of the inverse function is the domain of the function. If we take a look at the direction of the inverse function, notice that the output, it is a variable of x, which notice that that is what we plug in into the original function of f of x. That was the domain of the original function. In other words, the domain and the range, they switch locations between a function and its inverse function. Because notice that what we plug in to the original function is what we get out from the inverse. And what we get out from the original function is what we plug in to the inverse. So the domain and the range, they switch between a function and its inverse function. Let's take a look at some examples. So here we are given two functions, f of x and g of x. And what we want to determine is, are these two functions inverse from each other? If these two functions are said to be inverse from each other, then the domain and the range, they need to switch locations. Let's take a look into the function of f of x, and let's start by plugging some random values for the variable of x. Let's start by plugging in the value of -1. When we plug in the value of -1, the output is -3. Let's choose another value. let's choose 0. Let's plug in 0 into our function. Then the output is 1. Let's choose one more number. Let's choose the value of 1. Now let's plug it in into our function. Then the output is 5. Now to see if g of x it's an inverse function, we're going to get the values that we got from the range of the original, and we're going to plug into the function of g of x. And we want to see if when we plug in the variable of y, did we obtain the original x back. So let's start with the value of -3, and let's plug it in into g of x. When we plug in -3 into g of x, we have an output of -1. And this is good because notice that the range of the original, it is the domain of the inverse, and the domain of the original, it is the range of the inverse. They switch locations. What we have shown here is that when we plug in the value of -1 into f of x, we obtain -3. But -3, when we plug in into the function of g of x, we obtain -1 out. Now let's see if this is the same for all the other values that we have in our table. Let's check the value of 1. Let's plug in 1 into g of x. Then we get an output of 0. And notice that the match one more time. The range of the original, it is the domain of the inverse, and the domain of the original, it is the range of the inverse. When we plug in 0 into f of x, we obtain a 1 out. And when we plug in 1 into g of x, we obtain 0 back. Now let's check the value of 5. Let's plug in 5 into g of x. When we plug in 5, we obtain 1. Then notice that one more time, the domain of the inverse, it is the range of the original, and the domain of the original, it is the range of the inverse. When we get the value of 1 and we plug it into f of x, we obtain 5. And when we got that value of 5 and we plug it into g of x, we obtain 1 back. We can plug in infinite values into these functions, but I think 3 are sufficient to show the domain and the range are switching location between f of x and g of x. And because this occurs, then we can say that f of x and g of x are inverse functions. And now that we have shown that they're inverse functions, now let's try to see, is there any relationship between their graphs? Now let's take a look into that. So here we have the graphs of f of x and g of x, and the line y equals 0. In red, we have the function of f of x, and in blue, we have the function of g of x. Now to look at the relationship, let's pick one coordinate point for f of x. Let's identify the coordinate point of 0, 1, which we have it here. And for the inverse function of g of x, because the domain and the range, they switch location, then the coordinate point becomes 1, 0, which we have it here. Notice that we get the coordinate point 0, 1, which is displayed in pink, and we reflect it over the line y equals x. We obtain the location of 1, 0, which is displayed in purple. Is this something that occurs in every single coordinate point? Let's take a look at another one. Now let's take a look at the coordinate point of 1, 5, which is right here. And if the domain and the range they switch, now it becomes 5, 1, which we have it here. Note that the same relationship holds true. If we get the coordinate point of 1, 5, and we reflect it over the line y equals x, notice that its new location is 5, 1, which is a coordinate point in g of x. And this is the same if we would have chosen another point. Let's choose -1, -3, which we have it here. And for the inverse function, we will get the coordinate point -3, -1, which we have it here. We have the same relationship. If we get -1, -3, and we reflect it over the line y equals x, notice that we get its new location at -3, -1. And this is something that will always be true for any function and its inverse function. And the relationship is that the graph of the inverse function it will always be the graph of the original function reflected over the line y equals x. And this is true because of the relationship that we showed previously between a function and its inverse function. The domain and the range, they will switch locations, and that creates a reflection between the line y equals x. Hello. If you would like to continue learning about mathematics, you can check out the videos on the left.